is Sujan. I'm from Max Planck Institute for Biogeochemistry. Here we have been developing a model data integration framework for mostly terrestrial carbon motor processes. Okay, let's see. So is my slide moving? Are we in the next slide?
Yes, it's moving.
Okay, so basically, I think I don't need to convince anyone here that there are big misfits between models and observations. And we assume that it's coming from our lack of knowledge on the modeling of the processes as well as using data therein. So basically, I think if you think about the reasons of poor performance, you would think that we are doing simplistic representation of complex processes. We have rigid model structures. And also, as a third main reason is limited integration of observation data set into our modeling frameworks. And if you look at any modeling system, if you look at this nice figure from Liu and Gupta, really old figure now, there are different components of model. Basically, there is input, there is initial condition, there is parameters, which are mapped through the system of equations to produce an output. And basically, I think here we have seen that every component of the model leads to certain output and leads to uncertainty in the output. So what we wanted to do is extend the boundary of this system and also include the observation as well as observation operators that would lead to one unified system of having different input, different initial condition, different model formulations within one system, which you can use to understand water carbon processes. We named it SINDBAD. There is acronym here, but it's mostly to do the biogeochemical processes. It's not a land model, it's a terrestrial ecosystem model. And we don't do data assimilation strictly in the sense of correcting the states, but we change the model parameters in order that we match the states and fluxes coming out of the model with the observation. So just want to mention that the code is now public. It's in GitHub. There is a homepage. The paper is as a preprint somewhere. We need to submit and have it out. But the system has been there. We've been working on it for many, many years, and I will show you some results today. So we use the system. It's not one model, but we build different model structures to do the experiments that is suited for the scientific goal. So I'll just show you two examples here. We have a global model and an ecosystem scale model. In the global model, as you can see with the complexity of the figure itself, we have fewer soil layers, smaller processes. We only have water cycle because we want to understand the water cycle processes. We have vegetation, but it doesn't have productivity, and it only has a structural function. In the ecosystem scale, we have a model. It's built from the same framework where we have the carbon cycle, not only with GPP and transpiration coupling, but also through the full carbon cycle flow within different organs, and also coupling for root water uptake, competition between root water uptake and light, and so on. So we build these two model structures. The global one, we can summarize as a low complexity, has less data, but we use it for the role of vegetation on water cycle, mostly on the structural role. And we use the observation of ET, terrestrial water storage, runoff, soil moisture, and additional water equivalent to construct the model parameters. At the ecosystem scale, we use the FluxNet fluxes, let's say. And on top of it, we use the remote sensing to understand the role of remote sensing or the value of using remote sensing data. But here, the feature is the prognostic carbon cycle competing for different resources. And in both these experiments, it's always key to SINDBAD is we tune the model parameters to different set of observations, not only one, but multiple observations in one loop. And we use a global parameter source algorithm. In the simple model, we have fewer parameters. In the complex model, we have more parameters. But even in the global model, we do globally static parameters rather than varying per pixel. In site level study, we do parameters per site. So basically, I'll show you some key results. So in the global one, we again do two experiments, one with vegetation and the other without vegetation. Basically, our aim is not only getting good simulation, but to understand the role of different processes within the model. So basically, we had a global model which was already calibrated. This is the correlation of just internal variation of terrestrial water storage. This is rather difficult to get globally. And we see that the correlation is already quite high in most regions globally. This is the model without the vegetation parameters that influence the spatial variability of this globally constant parameters. If you use the other model with the vegetation, you see that there is further improvement, which is seen by the difference on the top right here. So even on a model that has already very good performance, adding new information coming from vegetation improves simulation mostly in regions where the vegetation structure is a key feature. This has been explained in the paper, a couple of papers from Tina, already a few years now. And in the other experiment, what we do is we have FluxNet observations, 200 something sites globally. In the first round of experiments, we just use the fluxes coming out of eddy covariance and the derivations from therein. And in the second one, we do again the parameter calibration and use the NDVI from MODIS as well as the biomass measurements, either from in situ or globe biomass, to see if there is additional value of using remote sensing data. So just a quick summary, I have different variables here in different panels. Two experiments are the yellow and green from that I just explained. More bars to the right means most of the sites are doing well. And what you see is in terms of fluxes, both these experiments are doing equally well. But when you look at the states, it's very interesting that the model without the remote sensing of states, which was already doing very well with all the fluxes, was still doing very poor in terms of using in the carbon state. For example, the leaf carbon and FA power, as well as biomass, was really overestimated. So using biomass data, which are the green bars, and this is the modeling efficiency. So basically, using biomass data and also remote sensing NDVI can improve the carbon states in addition to the fluxes before. So what I wanted to highlight here is basically you can, if you are using fewer variables as a measure of the performance of the model, it's possible that you might get the variable right, especially if you calibrate the model parameters. That doesn't mean that all the other processes are also constrained. So using more diverse data is a bit more robust in terms of these kind of challenges. Having said that, I think there is value of using observation, but the model and parameters are unfortunately experimentally skill specific. This I think we also saw in other presentations today. So we wanted to go a bit further and start predicting the spatial variability of the parameters together together in the flow of the ecosystem models. Basically, what we do is usually we have parameter per site or per PFT, then we use some kind of PFT or climate mapping to make this site level parameters globally varying, and then we use the global model. But it's not guaranteed that these parameters will produce the response in the site. So basically, we wanted to reduce the overfitting of the parameters in the site and at the same time learn the spatial variability of the parameters. And this is for the complex model at site scale. So basically, we collected a set of predictors that would go through a neural network that would produce the number of parameters for each of the FluxNet sites, which you would use within the physical model, run the model would produce an output Y, and from this output, you do the mismatch with the observation and do the loss term. And because this is written in Julia, it's fully differentiable, so we could calculate the gradient of the model, sorry for that, and basically use this gradient to update the weight of the neural network and prediction of the parameters. So basically in one online learning, you could learn the spatial variability of parameters together with all the site level observations. And this
1
we
minute
did.
left.
Okay, thank you. So in best case scenario is the in-situ optimization where you really overfit per site. And on the right-hand side in this hybrid is the one where we actually learn the parameters on the go. And the aim of doing this is if you have acceptable parameters and you learn the response of the model and you learn the mapping from the predictors to the global scale, you could have a spatial variability of the parameter for all the pixels in the globe. But we see that there is slightly worse performance, of course, for the hybrid one, but in general, the performances are acceptable, probably even slightly better than the PFT that is commonly used in all the system until now. But we do see that for variables like above ground biomass, there is still challenge with machine learning methods without the right predictors. This is something that we are working on. So basically, we have developed a framework from scratch to do the water carbon dynamics. We can build different models with the same framework. And we can learn parameters from the observation, and we do well across scales. And if you have any comments or suggestions, I'm open to ideas and collaboration discussions here, because it's slightly different community for me. And with that, I would like to thank you.